Okay, welcome to your video lecture for section 10.8 on Laplace's equation. So one of the most important of all partial differential equations occurring in both pure and applied mathematics is Laplace's equation here, where we have the delta operator applied to a function u is equal to 0. In two dimensions, it just amounts to the second partial of u with respect to x plus the second partial of u with respect to y is equal to 0. And in three dimensions, it's just the 3 second partials with respect to u of all the spatial coordinates, all equal to 0. Laplace's equation is just the equilibrium version of the heat equation in multiple dimensions. Since there's no dependence on time in any of Laplace's equations, there are no initial conditions to be satisfied. However, certain boundary conditions are imposed on the bounding curve or surface of the region in which the differential equation is to be solved. The problem of finding a solution of Laplace's equation that takes on given boundary values is known as a Dirichlet problem, while finding u when the values of the derivative of u are prescribed on the boundary is known as a Neumann problem. So oftentimes, say for example, you want to know the equilibrium heat structure on, say, a rectangular pan. What you might know is the actual temperature on the various boundaries of the pan, or what you might know is how heat or temperature leaves, so the unit normals here, out of the pan. Okay, the former being a Dirichlet problem, the latter being a Neumann problem. Okay, so what we're going to do is just solve the following general Dirichlet problem. So what we have here is we have Laplace's equation, okay, where our domain here is going to be a rectangle with the point 0, 0, okay, and then the points A0, 0B, and AB in our domain here. And what we're going to assume is that the temperature is going to be 0 along this side, and this side, and it's going to be some function f of x on the top here. Okay? And we're going to solve it via separation of variables again. So instead of assuming u is equal to a big X times a big T, we just assume that u is a big X times a big Y. And we get this, again, similar structure to the wave equation here, which gives us the following two boundary value problems, one for x, one for y. We have the homogeneous boundary conditions giving us three boundaries that are 0, the two for x and one of them for y. X solves the same boundary value problem that it has in the heat equation and the wave equation, so we know that x sub n is equal to sine of n pi x over a, and the eigenvalues again are n squared pi squared over a squared. So to complete this solution regime, we simply have to solve this boundary value problem for y. Okay. We know that the general solution in this particular case, because the roots of the characteristic equation are both going to be real, we have exponential solutions for y. This is a bit cumbersome to work with, so actually we switch the constants from k's to c's and transform these into hyperbolic sine and cosine functions. The reason that works is because sine hyperbolic of 0 is 0 and cosine hyperbolic of 0 is 1, which means that our second coefficient is going to be 0 in a very same way as if we had sine and cosine there. So our y sub n's are given by these hyperbolic sine functions here, and thus our solution up to infinitely many arbitrary constants is given by this sum of the product of hyperbolic sine functions with regular sine functions. As before, we use our final boundary condition. This is going to be a little bit more tricky because sine hyperbolic is not going to immediately turn into 1 when we plug in y is equal to b. It just becomes this constant sine hyperbolic of n pi b over a. Okay? If we multiply by the nth sine Fourier basis function and integrate, we end up with Cn times the aforementioned hyperbolic function evaluated at n pi b over a is equal to the nth sine Fourier coefficient of f. And so if we solve for Cn, we end up with this guy here. And just as an example, if we allow a equal b equal 1 and look at some solution profiles, here I plotted on top one where f of x is equal to 1, what we end up with is a function that somehow grows to be equal to the 1 function at one of the boundaries and is 0 at all the other boundaries while satisfying Laplace's equation on the interior here. And in the bottom case, all I've done is made f of x equal x. So this function has to satisfy basically this linear function on the boundary and be 0 everywhere else, while again still satisfying Laplace's equation on the interior there. Okay, thank you.